So here we reach to pulse modulate and band pass modulate, which are two core kernel principle blocks that your communication cannot work without. Those are principle, essential. You cannot say, I don't need them, or I can replace them with other blocks. The first block is pulse modulate. What pulse modulate is? We mentioned here that up until after multiplexing, you have your data is in the form of bits. But now bits are something that the computer can understand, and he can do processing. It can do processing on them and manipulate them, compress them, encrypt them, multiplex them, encode them, which is super nice, awesome, great. We like it, we love it, we enjoyed it. But now I want to prepare my signal to be transmitted over a medium, over a wireless channel, over a copper cable or Ethernet cable. Now the cable doesn't understand bits, doesn't even recognize bits. If you just send bits over the cables, your bits will not propagate or go anywhere. So what should I do then in order to prepare my data, my bits, to be sent over a very long distance to reach my friend, and my friend receive them correctly, understand my message, and get back to me? You need something called pulse modulate. Now is the time to prepare your signal to be put over a transmission line, over a transmission medium, so that this signal can pass through the cable with minimum effect and minimum distortion, and can reach your receiver, and the receiver can decode it successfully and then recover the bits carried by the signal. So this is why we need it and what's it. Now, basically, you get the sequence of bits, zeros and ones here, and convert each one of them into a pulse shape. For example, you say, if 0 comes in, I'm gonna generate a rectangular pulse. If 1 comes in, I'm gonna generate another rectangular pulse. So basically here, you have line encoding for the signal. This is the moment at which you convert digital bits into electrical signals, and these electrical signals have to have some form. Now, we understand that we need to convert them to electrical signal so that the electronic devices can recognize them. Now we are out of the CPU of the computer, and we understand that now we are in the phase of dealing with electrical signals. But what shape of signals we have to use? What determines that? So what determines that is the property of the channel. Let's assume your channel is subject to distortion in time or frequency, or subject to synchronization errors or phase noise. These are all like impairments caused by your channel on your signal, and you want your signal here, the signal you choose here, you want it to be resilient, robust against these impairments, which means that when your signal passes through the impairments caused by the cable or by the wireless channel, your signal can still reach your receiver, and your receiver can decode it successfully. This is what it means to choose a proper pulse here. So for example, what possible pulse that engineers usually use? They can use rectangular pulse, they can use raised cosine pulse, square root raised cosine pulse, or any other shape of pulses, as long as you choose the pulse with a reason, your communication will work properly. But if you choose it randomly, without any reason or without any justification, then most probably your pulse will not be the ideal, the most suitable pulse to be used, and therefore you may degrade your transmission, reduce reliability, cause errors, and make it difficult for the receiver to decode it successfully. So pulse now is the moment where you convert your digital sequence into electrical signal, and you select a pulse that's gonna be suitable to protect your data from the impairments caused by the wireless medium or wired medium. And also you choose a pulse that can also determine clearly where your data starts, where your data ends, and how much time and duration it should take, and which frequency it should occupy. All these details are determined by the pulse. After determining this, you will start calling your signal baseband waveform. So now it's not bit anymore, it's not bit stream, it's waveform. Waveform because it's a signal now, electrical signal. Okay, now I have an electrical signal in the baseband domain. What does baseband mean here? It means that your signal has low frequency spectrum. It's around zero spectrum. It means that you haven't modulated your signal yet. Your signal cannot still propagate through the cable. Now, some might ask me why I cannot propagate my signal if I convert my signal now. My signal is signal now. My signal is electrical signal. It has energy. It has soul. So it's not body now alone. It can travel. Yes, it's electricity. I tell you the following. When you come to the channel here, the channel, if it's a cable or optical fiber cable or wireless medium, the channel in principle in nature acts and performs like a filter. And we all know filters have certain range of frequencies and certain response. So if your signal frequency is within the range of the spectrum of the filter, then your signal will pass through and it will reach your receiver. However, if your signal frequency is outside of the range of your cable filter, then your signal, no matter what you try, no matter what you send, no matter what you do, even if you bring all the electricity in the world, it will not pass. It will not reach your receiver. That's it. So again, understanding this, the channel here, which can be Ethernet cable, copper cable, optical cable, or wireless, the air, the channel acts like a filter. It's basically a filter. It means that it has a response. This response can only allow certain frequencies to pass through. If I want my signal to pass through this cable or pass through this wireless medium, I need to prepare it for that. I need to make sure that the frequency of my data can reach to that frequency within the range of the filter so that it can pass through and reach my receiver. So that's why we have a process now called modulation, band pass modulate. Band pass, now we are not in the baseband. Baseband, it means low frequency spectrum. But band pass modulate, now you shift and you change the properties of your signal so that you can put it in a spectrum, in a location in the spectrum where it can pass the filter of the channel and reach the receiver successfully. This process is called modulation. Now, when you hear the word modulation, you get confused and you get scared because you have never used it in your daily conversation life. Yes? Have you ever used the word modulation while you are talking to your friend? Never, ever. And usually, even when you are writing, you never use the word modulation. So now, these technical terms, if you don't understand their meaning and like what they mean exactly, you will always be confused, no matter how many how many courses you take, no many how many books you read. Even when you read books, they never explain this. Why we call it modulation and what's it exactly? They just jump quickly into mathematical equations and how the process is done, but you never feel or get the sense of why we call it modulation and what does it exactly mean. So if you go and put the word modulation in the translator and search for it in the dictionary, you will find out that modulation means changing things, modifying things, adjusting things. So if we link the word modulation with changing, then now we can understand that whenever I read the word modulation, I should think of it changing. But changing what? Changing the properties of a high frequency sinusoidal carrier according to the incoming information that I want to transmit over a channel. Again, modulation is changing the properties of a high frequency sinusoidal signal that I want according to the incoming data that I want to transmit over a certain channel. This is what modulation is. If you forget the word changing, it means that you have some lack in understanding communication. Some people, they define it mapping. Some people, they define it multiplication. If you search on the internet and just see how people explain it and how they give a very narrow definition that can only cover a few cases for modulation. While modulation, in its general sense, it means changing any property of a carrier signal according to the coming information so that it can pass the wireless medium successfully. This is what modulation is. Now, one thing I need to define here, what are the properties here? You tell me it's changing the properties of a high frequency carrier signal. Now, what are these properties? So when we talk about high carrier sinusoidal signal, we usually talk about amplitude of the carrier signal, the phase of the carrier signal, the frequency of the carrier signal. So imagine you can change amplitude or frequency or phase of the carrier signal. According to what? To the incoming information. If the incoming information here is a rectangular pulse, let's say representing 1, then you can make the amplitude of your carrier, let's say reaching plus 10 volt. If it is if the incoming information here, let's say 0, you don't have information, it's 0 bit representing 0 rectangular signal, it means you are not transmitting anything, then in this case your carrier frequency can be a signal of voltage equal to -5 or 0 or 1 or whatever. Now you embedded your information that you have it in the baseband, which is represented by the electrical signal, you embedded this information into a high carrier frequency sinusoidal signal that can convey the sequence of information that was encoded in the electrical signal here. So this is why we need modulation. Why I needed this step? Because I will not be able to transmit my data and make it go through the channel if I just send it as is. But when I put it in a carrier frequency and this frequency is within the range of the channel filter, then I make sure that my signal will pass through. What's more important is not only my signal pass through, but the information encoded in the electrical signal here, I want them to be encoded in the electromagnetic signal that gets out of here. And the electromagnetic signal here is the high carrier sinusoidal signal. Here you get electrical signal, but once it reaches the antenna, the antenna's job is to convert electrical signal to electromagnetic signal. So we know from physics 2 that if a current passes through a cable, then the cable generates electromagnetic spectrum around it. And this is what we call the radiation spectrum of the antenna. Think of this like the access point antenna inside your mobile phone, inside your home, or the antenna inside your mobile. So the job of the antenna, it's a passive element. It converts electrical signals into electromagnetic signals that can propagate through a transmission line or through a wireless medium. You cannot see them, you cannot feel them, but those are the signals that are always surrounding us, carrying the information from one point to other in order to enable us to convey these information successfully and decode the data carried by them. After the bandpass modulate, you have frequency spread, which is optional. We don't always use it, but the job of this block is to make sure that your signal, first, it can spread your signal over a very large frequency, which makes it what? Makes it first secure, because now nobody can see your signal. And second, it makes it more robust against narrow interference. Suppose, for example, you have a signal at frequency F1, and there is another interference source that's affecting and concentrating its interference at F1. So if you transmit your signal as is like this, then your signal will die. Your signal will just get suppressed by the interference source, especially if it's transmitting this interference signal at a very high frequency. To avoid this from happening, what you do is you just spread your signal over a very large bandwidth and make sure that the power of the signal is below the power of the noise after you multiply it with a certain sequence. Once you do this, then if there is an interference source that affecting certain spectrum with certain amplitude, then the impact of this interference on your signal, which is spread now, is going to be very minimal. And therefore, at the receiver side, what you do, you just you multiply by this sequence that's used at the transmitter. And then since now you pass the channel, now your signal is in the receiver device, it's no longer in the channel, you are not afraid of interference now, then you multiply it by a sequence that can allow you to return the signal back to its narrowband domain, not the wideband domain, which is spread below the noise level. So we now understand the frequency spread. There are two types of frequency spread. There is CDMA, code division multiple access spread, where you multiply by a code, and there is frequency hopping spread, where you keep jumping your signal from one frequency to another in order to spread your interference and make sure that if there is an interference source, this interference source doesn't kill your message. And after that, we have final block called multiple access. Multiple access is the process where you multiplex different users on the channel. So you think you are the only one who's communicating and want to access the internet when you are inside your home, or when you are inside your office, or when you are inside your workplace. No, you are not the only one. You have colleagues, you have employees. All of them are connected to a wireless access point, for example, and all of them want to access the internet. So this multiple access process is the process that coordinates and organizes when the users are allowed to access the spectrum, when the users are allowed to transmit their data. Without this, you will not be able to serve more than one user. So this multiple access process is very critical, very important A process in order to serve more than one user simultaneously while meeting the requirements of all the users, while taking into consideration the services and the applications they are using. This is multiplexing. And then you go now to the analog circuit. Analog circuit, here you will have power amplifier and some other devices, filters, and some others until you reach the antenna. And the antenna just converts your signal to electromagnetic signal, and you just transmit it over the air, the wireless channel. Since you prepared your signal to pass through this filter, which we call it the channel, eventually it will reach your receiver, and your receiver will capture what? The antenna of your receiver will capture the electromagnetic energy. It's gonna be tiny amount of energy, extremely small. Assume you here transmit your signal with 20 dB or 30 dB. Here you will receive your signal maybe sometimes with minus 90 dB. Minus 90 dB. Imagine the amount of tiny amount of signal. How much insignificant the signal is, and still your receiver is able to recover your message from it. This is literally like unbelievable. This tiny amount of electromagnetic spectrum, once it hits the antenna, it generates a current. This current passes through here, it comes to a circuit, analog circuit. The first thing that it passes through is low noise amplifier. Low noise amplifier, your signal is extremely small and you cannot even recognize it. So the first step is to amplify it a little bit more. Give it some energy, some power so that I can deal with it. And your receiver is so powerful that it can decode the signal encoded on top of this tiny electromagnetic signal. And then after that, whatever you did in this, whatever you did at the transmitter side, you just reverse it. You do the things in reverse. If you have multiple access, you have also here multiple access to distribute the data to different users. If you have frequency spread here, you have frequency despread. If you have modulation here, you have demodulation here. If you have pulse modulate here, you have to detect the pulse here. If you have multiplexer, demultiplexer. If you have encoder, you have de-encoder. If you have encryptor, you have de-encryptor. If you have source encoder, you have source decoder. If you have ASCII code formatting here, you have to use the same table over here so that you can map your signal correctly. Any mistake, any misunderstanding, or lack of information sharing between the transmitter and receiver will cause your signal, will cause your message to be drop out, to be like misdetected, and accordingly you are not able to receive the message correctly from your transmitter. So imagine how complex the communication process is, how sensitive to all these impairments. Beside that, you have synchronization issues. You have oversampling here. You have analog to digital conversion. You have so many other blocks that I am not talking about here. But I just explained the core blocks that if you just know the why we need them, you can now at least get sense of what's going on in communication systems. These things are happening in your mobile phone, in your PC, in your laptop, each and every time you send data. And this is described irrespective of the networking level, of the MAC layer level, of the application level, of the software level. This is just what's happening at the physical layer. So imagine how complex, how comprehensive, how things are interrelated to each other and affecting each other. And this is just the block diagram of a typical simple digital communication system that we usually study it in a course called digital communication. You are not gonna go deep into all of these things. You are not gonna you just learn the basics also here. So usually people who go for PhDs, and after that they are gonna be able to not only understand and and study these in detail and deeply, but also invent and come up with new techniques and methods that can even perform better than the existing methods that were used in the literature. So this is the basic description of a block diagram of digital communication system and